Today we're going to continue our discussion of nuclear chemistry with section 2010, nuclear stability. And I'll give you a few seconds to copy down these notes. Okay, so the question is, why are some isotopes stable and others are not? Is there a way that we can predict this? So that's what we're going to be taking a look at today. And one key term we need to know is nucleons. This refers collectively to the protons and neutrons in an atom's nucleus. So when I talk about nucleons, I am talking about just protons and neutrons. And in the nucleus, one big thing that really does puzzle scientists is the protons are positive and the neutrons are neutral. And protons being positive, remember, like charges repel. And so you would think that these positive charges would just push each other away and the nucleus would blow apart. Well, what they have found is that they believe that the neutrons are basically a buffer between the protons to prevent them from repelling each other and pushing each other apart. The neutrons act as a buffer. And there is in the nucleus what's called the strong nuclear forces. These are the forces that hold nuclear particles together. They act over very short distances because these are very small particles, very close together. And really, these strong nuclear forces are a mystery to scientists. They really do not know what causes them, where they come from, or anything like that. But I think the Bible gives us a clue, because in Colossians 1:17 in the NIV, it says, "He is before all things, and in him all things hold together." This verse really gives me a picture of just God holding all of the nuclei in the universe together. Okay. And so I think that is part of the answer. I think this is just one of those mysteries of God, that he just holds everything together. Now, what they have found is that there is what is called a band of stability. And this band of stability identifies those nuclides that do not undergo radioactive decay. And the graph for this is found on page 510, and it's graph 2011. And I want to take a look at this graph real fast. So here is the graph. Oh, and it fits nicely right there. And the red is the band of stability. On the bottom, we have atomic number, which is the number of protons. On the side, we have the number of neutrons. What is found is that this kind of makes a nice curve. Now, this line down here, this is a 1-to-1 ratio of protons to neutrons. And we find that elements with fewer protons, that they are the most stable when they have this 1-to-1 ratio of protons and neutrons. But as we go up in atomic number, we find this line is actually about a 1.5 protons, or 1.5 neutrons to 1 proton ratio. We find that in order for the nucleus to be stable, we need more neutrons than protons, and we approach about a 1.5 ratio there. That is because of this shielding effect that the neutrons provide. And so we do, in fact, see that. So this is the band of stability. All of the yellow is radioactive isotopes that they have graphed. So the question I have here is, oh, my sun is coming out. Are cobalt-60 atoms radioactive or stable? Well, to answer this question, we have to look at the graph. Now, we also have to know that cobalt-27 has 27 protons and 33 neutrons. So if we find 27, right? Yep, 27. So this goes by 5, so it's about right here. 27 and 33. And we go up to 33, so 20, 25, 30, 35, 25, 30, 33. It's just a little bit above there in the yellow. So the answer is it's radioactive because it is outside the band of stability. It's just a little bit above that band of stability, so it is radioactive. Now, I'm just going to adjust this here. There we go. Another thing scientists have observed, and I'll give you a few seconds to copy this down. They have come up with the nuclear shell model. Remember, our electrons occur in shells. And remember that with a full shell, it's very stable. That's where we get our noble gases from. So the nuclear shell model says a model stating that protons and neutrons in an atomic nucleus exist in different shells within the nucleus, much like electrons in their shells. And they have found these magic numbers. This is the number of nucleons, either protons or neutrons, in a full nuclear shell according to the nuclear shell model. And what they have found is that if a shell is full with one of these magic numbers, then the nucleus is more stable. And the magic numbers are 2, 8, 20, 28, 50, and 82. And they have found that if there are either the protons or the neutrons have this number, the nucleus is going to be stable. And it's doubly stable if it has like both its neutrons and protons are these numbers. So there's a whole list of these in your textbook. I'm not going over them, but just something really interesting going on there with these magic numbers, that they can predict the stability with them, much like they can with electrons. And so just something interesting to throw out there. So that's really all I want to say about nuclear stability. Let's wrap things up by talking about section 2011, solving problems with radioactivity detection. So copy down these few notes. Okay, so one reason we need to study radioactivity is because of radon-222. It's found in nearly every building and has been linked to an increased incidence of lung cancer. So there is radon-222 outside, okay? And it's in a concentration of about 0.4 picocuries per liter. So there is some outside. Now, radon is a decay product of uranium, and it decays through alpha decay to produce polonium-218. Now, this is naturally everywhere. It's when it gets to a certain concentration that it can be dangerous, okay, and it has been correlated to an increase in lung cancer. So it has been suggested by the EPA, the Environmental Protection Agency, that homeowners provide better ventilation in their houses if radon reaches 4 picocuries per liter. And they definitely should. And even between 2 and 4, it's a good idea. Now, how would you test for this? There are actually test kits that you can get from hardware stores that you would put in your basement and collect a sample following the directions on the package, and you would send into a lab to find out. And then you, depending on the value that you get back, you may have to correct the problem. And according to your book, it usually costs about $1,200 to correct the problem, which is not a huge cost. Okay, so that is a danger. And I do want to show you the map if you haven't looked at it yet in your book. Here is the map, and those areas in magenta are where there are the highest levels of radon. And actually, we fall in one of those areas. So it is something you should be aware of, that it is a possibility that you could have high levels of radon in your basement and in your house. So just something to be aware of. I know I have not checked for that at my house, but maybe an idea, okay? So maybe you've heard of somebody who does have high levels of radon and has to have one of these ventilation systems in their basement. Well, that is it for today. I had put that we were going to do page 523, question 24. I decided we don't need to do it. It's not really on the test, and so a present for you today that this is it. So short lesson today, and I'll be back next time.